Good afternoon, ladies and gentlemen. Welcome to TechGig webinar series, our endeavor to impart techies. We believe that sharing of knowledge is the key to enhance our skills and grow us as professionals. With this principle in mind, we have initiated a series of webinars conducted by industry experts to give you all a crisp insight of various domains. The topic of today's session is Big Data Analytics. Can it deliver speed and accuracy? Our guest speaker today is Mr. Gurinder S. Grewal, leader, Real-Time Big Data Platform, eBay Inc. Gurinder leads Real-Time Big Data Platform at PayPal. He has 18 years of experience building, scaling very large complex distributed systems at various companies. He has served various leadership roles in large e-commerce, telecommunication, and networking companies. He was a key member of the architecture team that scaled eBay's first-generation architecture. So without further delay, I introduce you all to our guest speaker. Over to you, Gurinder.
Thanks, Moini. Hi, everyone. Welcome to the session. What we're going to do today is I'm going to share with you the learnings and the challenges that we faced as we embraced big data at PayPal. I assume everybody can see my deck. Before we get into the learnings, I want to share a profile about PayPal so that we know in the context of the system that I'm talking about. So for the folks who who don't know about PayPal, PayPal provides a platform for users to exchange money. One of the value adds we have that we allow our users to exchange money fast and in a safer way. If you actually think about these two things, fast and safer, these are two conflicting requirements actually. And that's going to be the theme of our talk today as well. And I'll talk more about why safer and fast or a speed are conflicting requirements further in the slides. So about PayPal, we have about 123 million active users. By active users, we mean a user who has at least sent one payment throughout last 3 months. So there are a variety of users. There are individuals, merchants, and so forth. We have presence across the globe supporting multiple currencies. What really matters is at any given minute we process about $300,000 worth of payments. What that really means is the responsibility that you take of moving actual money between two hands, right? So in order to move this money, there's a lot of back-end analysis that happen, online analysis that happens. And in the context of the system that we're going to talk about, we process about 2 billion events per day. And in terms of data scale, as you can see, there's 12 terabytes of new data added every day. Part of about 60% of the data is behavioral data, or observational data. Observational data is when you're monitoring your systems, monitoring how your applications are behaving, and monitoring how your business logic is performing. Then there's operational data and transactional data. The load on the system, on the real-time system, is pretty significant in terms of the data lookup queries. We process about 500,000 queries per second. At the same time, the response time SLAs for the system are pretty stringent. So 100 millisecond average response time is to process any given request and provide an answer if the current interaction from the user is acceptable or not. So you can slice up this 100 milliseconds into further buckets. If I was to run an analytics logic on 100 milliseconds, that means there's only a slice of this 100 milliseconds available to load the data. So the idea is that you need to load lots of data and you need to load it really fast. And these two requirements keep growing. As we move through the time, the response times are becoming more stringent. Everything is getting more optimized. And at the same time, the amount of data that we are dealing with on ongoing basis, the data is growing. So the requirements are always get more data, get it faster, right? And given the scale of this data, we are really talking about big data, because one of the questions that normally comes up is, what is big data? When do we say that I have a big data? What's the threshold? Threshold is basically once you reach a point that you can't analyze your data in real time, and when you have to really employ offline systems to analyze your data, you are actually embarking into the territory of big data. So then the question arises that in the industry we have been doing this for all along. There was always offline batch processes that were processing the data. There's online systems that are processing data. So why big data now, right? The differentiator is that the scale of the data is growing. There are new tools that are emerging that are allowing us to process this data in more efficient manner. So that's a key differentiator. So it's not that big data is new, it's been there, but there are new tools that are opening up new possibilities to analyze this data efficiently. So about 3.5 years ago, we started looking at PayPal, we started looking at big data and started taking it seriously. At that time, for most of the folks, big data was a buzzword. It was a new emerging hype, you can say, in the industry. And there were a lot of doubts around if this is a real thing or not. And I can truly tell you, after embracing the new tools, we realized that it is a reality actually. It's not hype anymore, right? So when we started putting together a strategy about 3 years ago, how to bring in big data into PayPal, there were questions rising. How do you really define big data? What is big data? So when you put together a team of diverse people, because you'll need diverse talent to put together a successful solution, there's different thoughts that come into your mind. For some folks, big data is about storage. It's about storing petabytes of data. For other folks, it's installing thousands of machines in a cluster. If you talk to data scientists, they are thinking about diverse analytics and so forth. But then if you take a few steps back, what does it really mean for the business, right? So far the aspects that I talked about, those are very low-level aspects. Those are the aspects if you start looking in silo. So to the business, what really big data means is that the ability the system is going to give us to come up with large number of rich characteristics. By rich characteristics, I mean is the rich, intelligent data points that you can feed into your decision systems to make accurate decisions, right? So that's, in the end, that's really what it means to your organization. Now, looking at the timeline, if we look back about a few years back, even not too long either, as the online ecosystem became more is being used by consumers more, there are also bad people emerging into this space, right? So there are different types of data we started collecting. There are more channels through which you can go online. You can go through web browsers, mobile phones, and so forth. So from a variety of angles, either you're doing risk management system or you're handling a marketing system, there's a need to do sophisticated analysis on this data that we have. It's not about simple rules, blacklists or white lists based on which you can do decisioning. So as the time went on, the analysis started getting complex. At this point, we are at the juncture where we are doing a lot of history analysis, but really analytics is moving more into social graph analysis. Not that people don't do social graph analysis, there are companies who does that, but it's not a mainstream analytics as of yet. There are no champion technologies out there that allow you to do social graph analytics. Just to clarify that point, if you think of any other analysis, there are products like Teradata, there's products like Hadoop, which will allow you to do the normal analytics or less complex analytics, but social graphs are still a challenge. So that's where we, from my perspective, I see where we are as an industry when we do analysis. The key point is that as time goes by, the data infrastructure is growing because of the volume, velocity, and variety of the data, and so are the expectations. Like we talked about, we need to make decisions fast, we need to make them accurately. So let's take an example why decisions have to be made quick. Here's an article that was posted back in May of 2013. There was a crime committed in New York where $45 million were stolen within a matter of hours. Then in the same article there was an example of a fraud where 36,000 transactions happened worldwide to steal $40 million. Now that's a lot of money, right? If we had a system which could detect this fraud in timely manner, this damage could have been reduced. So really what we are talking about is if you could react to this fraud fast enough, the faster you react to the fraud, the higher the business value you give. So there's different type of actions. You can have preventive actions. Preventive action is when you can stop bad guys coming into your system altogether. But if you're going to do this, then decisions must be damn accurate because you don't want to leave any money on the table either. You don't want to prevent good guys coming into the system. So preventive actions are the most valuable actions, but the accuracy becomes really important at that point. But then there's another strategy. You could take some risk. This is where the speed comes. This is where you have to sacrifice the accuracy that maybe in certain environment I can't achieve the accuracy, so I let some money to slip by at the risk of that my users are getting bad experience as well. But you can take fast decisions at this point, right? But the idea is as the time to make decision grows, the business value goes down. So that's why the decisions have to be made quick. At the same time, decisions have to be accurate. So let's look at this classic fraud use case. It's a classic use case where a credit card is being used in very short amount of time in 3 different locations of the world. If we were really to shoot for speed, then my detection system would say, or would have an analysis saying, I should really block this card because there's no way this user can move across the world within 5 minutes. But is that enough? That's not enough. You need to go deeper. That's where we need to probably look into historical behavior of this user. Historical behavior might say the user lives in the US. Maybe user's wife was doing the shopping on their favorite merchant site. She purchased something. Then user's kid is going to school in Europe. and he purchases books from certain device all the time, and that's exactly what happened. And user himself is traveling to Asia and just purchased a lunch. So now if you combine the speed and the historical behavior, the decision is going to be different. Now it all of a sudden looks like it's a legit use case, right? So you have to, the point is that you have to have both speed and accuracy, but you have to strike a right balance. So next thing is, now I'm going to start, now that we understand the importance of both speed and accuracy, let's get into the how we use big data, or how do we leverage big data in an efficient way to make decisions. So anytime we talk about big data, there's 3 V's that are being talked about. There's a velocity, variety, and volume. Velocity is, when we talk about velocity, we're talking about the data incoming into your system, or the rate at which data is changing, right? And there's a need that you need to analyze this data as is flowing into the system. And you need to make sure once you have analyzed the data can also be consumed by your decision-making systems in right time. Then accuracy, this is where the powerful analytic techniques are being used. There are new systems, new technologies now that allow you to crunch structured, unstructured data and implement very sophisticated complex logics. The point here is that to shoot in accuracy, we're looking at processing or looking at the details of the data, right? Both aspects are fine, speed and accuracy, but then there's third aspect that we have to keep in mind. The cost has to be efficient, because you don't want to spend too much money to save low amount of money. So really what it means is, if you want to make efficient decisions, it is a function of 3 different aspects. It's a function of accuracy, speed, and cost. So now let's lay out these 3 different aspects onto our data strategy. How do we come up with a big data strategy to meet all these requirements? In order to lay a data strategy, you need to start looking at data in different states. There are generally 3 states of the data. There's a data in motion. Data in motion means the data has left the data source and it's making its way to the data store, where it's going to live and where it will be used. And during this transit period, the data may live in some memory buckets or some temporary, even persistent storages. That's the data in motion. The data in use is when data has made it to its source of truth data stores. Source of truth data store is the data store that you always rely to seek the truth, where the data is going to be in consistent state. Then third state is, which is out of the context of this data strategy, is data in rest. That's when the data has been backed up to the offline storage, like tape backups and so forth. So now let's start going bottoms up. When data is in use state, that's where you can shoot for accuracy. That's where the data volumes are really high. And I would call that offline environment. This is where you would run complex logics on your data. So here, another aspect is that you want to keep the data always in an append mode. You never want to overwrite your data. The key principle that you want to use is that the data that you have acquired, store it as it is. Because we don't understand our data at very first sight. It takes time before we build an understanding on our data. For example, if you were collecting clickstream data, clickstream is where you're capturing the URLs. You might look at where this URL was clicked from, which URL this user is clicking from. Maybe those are the only two data points that are of interest to you today. And if we were to transform this data and only store those two values and throw away the original data, then there are other parameters in the clickstream data, but you just threw them away, right? So from that perspective, don't transform and throw away the original data. Keep the original data. Bubbling up one more layer is data in motion. Here, you want to keep very small amounts of data. Like we discussed, data in motion is data in transit. So the age of data can vary depending on your system. It can go from anywhere from seconds to hours. But don't try to keep months worth of data in the state. This is where you're going to shoot for speed. But speed and cost go hand in hand. The systems that are optimized for speed, the complexity grows for those systems and the cost goes through the roof. So this is our data strategy. Again, takeaway point is data in use is the state where you want to shoot for accuracy. Data in motion is where you want to shoot for speed. Now we're going to talk about computation strategies. So there are three layers that I would like us to think about. Going from bottom up, you have an offline environment where you do batch processing. And the nature of batch processing is that systems are optimized for throughput. This is where you can consume large amounts of data. And this is where you can do probably your historical event analysis as well. One thing I want to mention about events is when you start capturing data as events, like we just talked about in previous slide, not overwriting your data, but capturing as events means every single change that you saw in the data, you're capturing every single change. This becomes a very powerful tool for analysts because now you can give them point-in-time capability. Point-in-time capability means that it sort of like works like a time machine on data. Your analyst can ask a question to your system that how did a certain user state look like at a given time in the past. For example, how many email addresses this user had registered with us 3 months ago, right? Because you have captured data in as events and have captured every single change coming into the system, you could answer the question now. And with new emerging technologies that we have these days, capturing every single change is not a big deal. It was, people would roll their eyes if you're trying to do this 4, 5, 6 years ago. But as time goes by, storage is coming cheaper. We are getting very high computation powers at cheaper price. So yes, we are able to consume this data, and it's not so expensive to keep this data in storage as well. Now, the next upper layer is the near real-time processing. So from offline processing, you build some insights, you build some offline variables. These are normally your predictive analysis, historical analysis, very rich set of variables. But then there are some variables that you need to compute, some data that you need to analyze as events are flowing into your system. The nature of events is that event is something that has already happened, right? So normally event-driven systems are asynchronous systems. So what that really means is the user has already clicked on something, and after that event has been emitted out, and now we are getting a chance to analyze that event asynchronously. So for that fact, just that matter, it's a near real-time processing, not the real-time processing. This is where you would use technologies like complex event processing, and we'll talk more about that in coming slides. The data that you want to analyze here is very short time windows, normally hours, and this is where you shoot for high efficiency and scalability, because the number of events coming into your system can significantly grow. Because if you're monitoring every single change, because there's a difference in real time and near real time. The real time processing is normally the transactions that are happening in your system, right? But in near real time, we are monitoring, observing a lot of stuff. There's a transactional data that's coming in, there's a observational data that's coming in, operational data that's coming in. So here you want to shoot for efficiency and scalability, and there are challenges around scalability. I'll share that with you in coming slides. Then there's a layer on the top, which is real-time processing. This is where we want to shoot for optimal speed, the ultimate speed. The SLAs, response time SLAs, are very stringent. This is where we need to achieve high availability of the system as well. The computation that you want to do in real time has to be very simple, and this is not the place where you want to shoot for accuracy, because accuracy really means analyzing large amounts of data. Only then you can make accurate decisions. So in order to achieve accuracy, you rely on your underlying layers. You rely on your offline variables plus online variables, and here you're just looking at what's coming in the context of my request. And computations here are really transient, they're short-lived for the lifetime of the user sessions. Generally, you don't feed this data into your downstream layers. You normally consume data from downstream layers. So that's our, so we talked about our data strategy, we talked about our computation strategy. Now let's look into the systems, offline systems and online systems and their ecosystems, and I'll talk about some aspects, the key learnings from here, and in certain cases the talent that's required to build these kind of systems. So offline system, I'm going to specifically talk more about Hadoop technology stack, and a little bit about the data warehouses as well. So the very first thing you want to do with the offline system is think about where is my data is going to come from, because once you start recognizing where the data is going to come from, it's going to lay out the requirements for you, for the capacity requirements, what kind of processing I need to do, how I'm going to integrate this data, and so forth. So there's generally in the industry we talk about two types of data structures: structured data, data and unstructured data. The key learning is when you're dealing with unstructured data, try to use systems that don't require you to have understanding of your data. For example, there are two data integration technologies that I want to talk about. One is our classic ETL processes, ETL technologies. ETL stands for extract, transform, and load. Extract means you're extracting data out of some data source, then you're doing some transformations. The fact that you're doing some transformations on data is that you have understood your data, right? Then after that you load the data into other system. So with unstructured data, the whole point is that we haven't understood our data yet. That's why it's unstructured. If we have understanding of their data, then we can lay out schemas for it, right? So the principle that you want to use with unstructured data is get the data as fast as you can into the system and let the data processing layer take care of transformation. So for this, we normally rely on Flume and Scoop. These are both open source tools. The data storage, generally for unstructured data, you want to dump it into HDFS. Then you also have HBase. This is normally where you would bring in your structured data. HDFS very good for unstructured data. So I won't go over every single box in this diagram. But another thing I want to talk about in Hadoop technology stack is scheduling and coordinations. This is a weak point in this technology stack. There are two main pain points with this area. Number one is generally when you start building Hadoop type of clusters, you can't really do a capacity planning in fine grain. You cannot do coarse grain capacity planning. What that means is you generally bring in over capacity. If you need 100 nodes, you might want to have 150 nodes. Why is that? Because as of today, with mostly open source technologies, Hadoop stacks, there's not sufficient quality of service tools out there. What that means is there could be 2 Hadoop jobs running. There's no way to guarantee which Hadoop job should take priority over other. So for that perspective, you want to have a buffer in your capacity. Another thing that's really lacking in Hadoop technology stack is the aspect of elasticity, because if you have large infrastructure, if you're not using it all the time, it would be ideal to give away that piece of infrastructure for other processing and borrow it when you need it. So these are two actually drawbacks that in this technology stack. Other than that, the power it brings is worth it. Now we talked about offline system, which is data in use. Let's talk about when big data is in motion. One thing I want to lay out before talking about big data in motion is a lot of times when you talk to people, we kind of draw a boundary on big data into like offline systems. Big data is not only offline system. Big data is all of your data is big data. So either it's in motion or it's in use, it is big data, right? So for big data in motion, there's a complex event processing technology that you could leverage. The basic idea is that you feed in these event streams into processors where you can do correlation of events. What that means is you could say if user just logged in and then user clicked on show items page, then I know this user is going to, what is this user going to do next? The idea is that you're, with CEP type of technology, you're always looking forward. What is user about to do based on the events I have seen? So you're always observing the present and trying to predict the future. Whereas on offline systems, you're always looking back on the historical behavior and then try to predict what's going to happen. So in complex event processing, generally events come in where they get filtered, aggregated, and so forth, and then you emit decisions out which can be consumed by your decision services. One of the principles in complex event processing is that you don't try to persist or keep those events, mean the historical events for historical lookups. It's like if you're dealing with the event, you looked at it, you just throw it away in the context of CEP system and do something, get some insight from the event, and maybe based on that insight you may generate next another event. And we'll take a look at an example in the coming slide. Generally these technologies rely on in-memory data stores to operate that fast. because like we talked about before in a couple of slides before, this is where you want to shoot for efficiency and scalability. The speed will only, you can't really rely on persistent data stores to build CEP systems. People who have tried this, the systems have failed. Or if you know of systems that are working based on persistent data stores, they might be very small scale systems, but when the scale goes up, then disk I/O can't really keep up with that kind of volume. So out of CEP system, you're storing some data in in-memory data store, you're sending events to decision service. At the same time, you could send alerts or some observational data, means how my logic is performing in the system or what decisions I made, asynchronously to message bus, which can be consumed by offline systems. So in a way, what you're doing is, here is you're building a feedback loop. Your complex event processing is notifying offline system that this is what I did. Then on offline system, you run a bad job at some product period and do analysis on what was done by complex event processing and feed the data back into complex event processing. For example, you could be running some sort of model here and say this is how my model is behaving, and offline system can say, okay, my model performance is degrading, hence I need to tune my model by adjusting some parameters, and then send the data back into the real-time system. So that's how you can combine both online and offline technologies. So one thing with complex event processing is the scalability challenges. Anytime when you talk about scalability, it's like, what are you trying to scale, right? The very first step is the tuning, the optimization. Are you optimizing for speed or are you optimizing for throughput? These are two opposite ends of spectrum. Now, if in the case of CEP, we are always optimizing for throughput. And throughput is a function of how many events can you process in CEP system, right? That's one aspect. The second aspect is, what is the workload to process this event? Because somebody can come and tell, I'm processing 1 million events per second in my system. But what are those events? What are you doing with those events? If you're just passing them through, you can process probably 100 million events per second. But if you start doing queries or start doing analysis on those events, then you might not be able to process 100 million events, right? So the idea is, the larger the workload is, the lower the throughput is going to be. So how, in terms of volume, there are well-known strategies out there in the industry that you can leverage. You can equally distribute the load across your cluster. This works very well for stateless architecture, share nothing architecture, where all the nodes are equal. They can perform, they can process a request, any request at any given time. They don't maintain any state. You don't maintain the state on the node itself. The state is maintained somewhere else. Actually, even this is another key point. Anytime we talk about stateless architecture, actually, matter of fact is the state is always required. It's just that the compute nodes don't maintain the state. State is maintained somewhere else. If it's maintained database, the database might become bottleneck. So mainly you leverage cache, in-memory caches for this. Anyway, another way to handle volume could be sharding your workload by key hashing. This works really well for stateful processing, but the caveat here is, let's take an example. If you're sharding your workload by users, and one of the users happen to be a merchant, and the merchant will have much higher volume than individual users, right? In this case, one of the nodes in your cluster will become very hot. It will be taking lots of load, right? So that's the caveat with sharding-based technique. So really you have to know your workload, you have to know your data, you have to know your customers' interactions to pick the right strategy for yourself. So actually event volume scaling is not a problem. The main problem, the challenge that comes with the CEP technology is how do you scale the event processing load? And I don't want this talk to become too much of a CEP centric. I just wanted to give you a flavor of why CEP scalability is complex. So I'll just very quickly walk you through this example, and then we'll focus more on big data. So one strategy you can take is that you can divide up your workload into units, separate units. And I view this as reversing your MapReduce job on Hadoop. So basically, and we'll talk more about that, how you reverse the MapReduce job. The idea is that if you can divide up your workload into smaller units and assign those work units to different processor nodes, means that you want to, instead of doing the whole workload on one node, you can say I will have a tiered architecture. Let's take an example. If I can split this workload into 3 different units, then I want to have a front-end machines which takes care of first unit of work, then hand over the next unit of work to second-tier nodes and third-tier nodes and so forth, right? Generally what you do is you try to do filtering on the data, because in CEP systems you don't always analyze every single event coming in. So it's not always applicable to certain all the aggregations. So there are different type of aggregation that you're doing by events, and those are done by filtering the events, right? And then, so the idea is to divide the workload work units into stateless work units and stateful work units. Stateful work units are where you do complex logic processing. And let me give you a concrete example, that way it becomes more clear. Let's say we built a hypothesis that whenever my customers use mobile phones, we believe our customers use mobile phones during non-working hours. Then if that's the case, then my business policy, I want to have a business policy that when user is on a mobile phone, and if they're in non-working hours, that's the point when I'm going to offer them coupons, either for restaurants or to go to movies and so forth. So in this case, what I really need to know is when does the mobile logins exceed the web logins, right? So I have already, I can already divide up my workload now. Right, so this is what I was talking about, reversing the MapReduce job. So you do filtering first. Is this a mobile event or web event? If it's a mobile event, then give it to mobile velocity processors. If otherwise, to web velocity processor. Velocity processor is nothing but that can keep account how many logins are happening in a certain amount of time. Then based on if the logins exceed certain threshold, then you can give it to your business rules processor. So that's just one example of how you can scale CEP system. There's many different ways. You really need to find the right strategy for yourself. But now we talk about online and offline systems. Really the key and the biggest challenge here is the data movement. If you're building large number of insights, the question becomes how do you move large amounts of data through networks and to multiple data centers. The data transfers can be very expensive, and the techniques that we use to move the data around are not very flexible. For example, ETL process is a very manual process. So I'm going to walk you through, this is one of the last slides. I'm going to walk you through the data movement optimization evolution that we had. The initial state of the data movement was when we didn't do any optimization. This is just to get a baseline. we were transferring about 500 gigabytes of data in 16 hours from one network to another network. Then we did optimizations. The key in the optimization was how do I minimize the number of bits that are moving across the network. So you can minimize the bits by compressing your data, selecting the right data format, make sure the data format is not too verbose. Even doing validations before moving the data. Am I moving the right data? Because you don't want to find on a live system, oh, I'm getting null values and so forth. So the key is optimize your data format, do all the validations you can do upfront before moving the data, and use the compression. Some people shy away from compression thinking it's going to slow down my system. These days compute power is so efficient that compression doesn't really slow down that much. So by doing this level of optimization, we were able to move 2 terabytes of data instead of 500 gigabytes in 16 hours. But the need is to move 10 terabytes of data in 6 hours. So what was holding us back in phase 1 was that the online data stores are not really optimized for parallel data loads or bulk data loads. They're more optimized for speed, quick lookups. So that's where we started having putting together a strategy, two-tier strategy, that you do offline data movement at full speed to a NoSQL persistent backing data store. And on top of that, you have in-memory data store, your cache, to which your applications are interacting with. So your applications can always be reading or writing data from in-memory data store and never feel or are never competing with the full speed bulk load that's happening on a NoSQL database. And you can lazily load data into cache, different strategies that you can apply. You can have a batch process. As soon as the data comes into NoSQL data store, you can push it into your cache. The idea is they separate the data store that your online applications are accessing from the data store that you use to move the data into. Okay. Very quickly, I won't go into details of next use case, but the thing is the power of Hadoop type of systems or combining online and offline computations really help you build very complex decisioning capabilities. Here I'm giving an example of graph-based decisioning. You can build social graphs because building social graphs is very time-consuming or very computation-intensive. So you can build them offline, bring them to online, and when you bring into online data store, as events are flowing into your system, you do incremental updates. Means if your graph was updated last midnight, then you apply all the events that happened since midnight till now to bring graph up to date. At the same time, you could be also computing aggregations around your graph at that point. And your reader applications can access this data really fast. Okay, so what do we get out of this whole talk, or what was the conclusion of this whole talk? That Hadoop is Hadoop type of technologies. They are best at processing variety and volumes of data, but they are not for real-time processing. For real-time, you really need CEP solution. That's where you can address your velocity. So both technologies complement each other. A lot of times there's talks if they're competing with each other. The fact is that they're complementing. So the key is that combine offline and online data, but to do that, your data integration is the biggest challenge. Needs a lot of optimization. The challenge comes from our online data stores are not tuned for heavy loads, heavy write loads or bulk loads. So what we have seen that you could solve complex problems using offline and online systems, just like what we saw in our graph example. So that concludes our talk, and I will open up the session for any questions you guys have. Okay, so the very first question is, why CEP in big data? The question is asked by Ram Rambo. So like we talked about, there's two aspects of big data, right? So first of all, let's not draw boundaries on big data. Um, so with big data, you want to handle velocity, volume, and variety. Just like we talked about in conclusion slide, you can shoot for variety, velocity, and uh, volumes in offline system. But at the same time, offline systems have time lag, right? There's always a time where the data hasn't reached your the offline systems. And just because of the nature of offline systems, because they're batch processing, the insights that you have built, they haven't been fed back into your decisioning system. So what do you do for the data that hasn't been yet consumed by your offline system? You need to analyze that using certain technology, right? And just the fact that we talked about when you're bringing data into offline systems, bring in form of events so you can keep the change history in your data. So CEP becomes technology of choice because it allows you to do complex processing on your events. For example, correlations, filtering, and so forth. The next question is, in offline analysis, you can slice and dice data in multiple ways. In ATM, use as example, you uses pattern to declare a series of transactions legit. How does PayPal decide on what to analyze and how to correlate? The question is asked by Abhijit. Actually, unfortunately, I can't get into too many details what strategy we use at PayPal to do our analysis. But the idea is we don't leave any data out. Whenever you talk to any analyst, be it a PayPal or not PayPal, the idea is as the data is flowing in, you want to try to understand data on an ongoing basis. Maybe first when you start acquiring the data, if you don't understand your data, yes, you analyze what you understand. And as time grows by, you're getting into deeper and depth of the data. So we really don't leave any data out. We try to analyze as much as we can, and that's where technologies like Hadoop are flourishing, because they do allow you to go wide and deep on your technologies. What is unstructured data? Khushbu Agarwal. Unstructured data is basically various forms of data. You could be crawling web to pull out the HTML pages. You could be storing feeds, Twitter feeds, Facebook comments, and so forth. Unstructured is anything for any data for which you haven't really actually understood the data and decided in which schemas I'm going to fit this data into. Which graph database you have used and why. Actually, the beauty of working for PayPal is, the reason I love working for PayPal is that any technology you give us, we know how to break the technology because the volume of the data that we have. So going back to your question, which graph database you have used? None, because there's no graph database as of today which can claim championship in the space. We have tried prototyping few databases, graph databases, but they were not able to scale. See, another point I would try to make here is there's a reason why companies like eBay, PayPal, Facebook, Google, they come up with their homegrown technologies. Because a lot of times when new employees join our company, they're always asking, why are you guys building in-house? Because the technology that exists out there, one thing that I learned is the scalability is very underestimated aspect. They don't really scale with the volumes that we have. And then scalability, once you start moving notches of scalability or availability, for example, if you have to go from 99.9% availability from 3 nines to 4 nines, it takes a lot of investment, takes a lot of tuning. Same applies with scalability. You can scale for certain data patterns, but then there's always outliers that you have where your system won't scale. So that's why so far we don't use any graph technology, and this is something we're trying to build in-house. Okay, what is CEP scalability? CEP scalability, as we talked about, how do you process, how do you keep up with number of events that you're going to process? Now, as we talk about the understanding data and doing deeper analysis, right? How do you scale for increased workloads? So I want to consume more events and I want to do more data analysis on these events. So this is where your workload is actually increasing. So that's what I meant by CEP scalability. What does HDFS stands for? HDFS is highly distributed file system. It's part of Hadoop technology. Okay, what is the concept of sharding? Rajat Jain. So sharding basically means share nothing architecture. What it really means is how can I partition my systems. So sharding applies all the way from data technologies or data stores to your application tier. When we are talking about sharding at the data tier, it really means how, so for example, let's say if you had one node which hosts all your data, how are you going to scale the system, right? And whenever we talk about scalability, there's two aspects. You can scale up or you can scale out. When you're scaling up, that means how much capacity can I keep on adding on the single node? For example, if you had a disk which can hold 100 gigabytes of data, maybe now you added a disk which can hold 1 terabyte of data and 10 terabytes of data. But at the same time, there are other resources that may become a bottleneck. For example, can you process or can you handle the requests for 10 terabytes of data? So at some point when you're scaling up, something is going to show up as a bottleneck. At that point, you need to start scaling out. So when you're scaling out, then you start using concepts like sharding. Then you can say, okay, I'm going to have 2 instances of my database, and first instance will have 50% of my data, and rest of the 50% will go to second instance of my cluster. So that's how you start sharding. Same goes with your application nodes. That's where the load balancing works pretty well. Okay, so next question is to optimize. What strategy would be the best, asynchronous or synchronous? I believe synchronous systems would take more processing time over asynchronous system. This is aimed at keeping the performance optimized. So generally when you talk about asynchronous systems, you optimize for throughput. When you're talking about synchronized systems, you optimize for speed. The reason is very simple. When you have a synchronous request, there is someone who has submit you the work, and that system or the user is waiting for a response, right? If you don't respond fast enough, there are going to be impacts that are going to go upstream. They're going to start bubbling up. For example, let's say there is a first tier, frontier application which sends a request to middle tier, and middle tier is serving the same request in 1 second today, right? If based on that, I did my capacity planning that on my frontier I only need 2 nodes. But what if the middle tier now starts taking 10 seconds? That means my front-end applications are now blocked. They can't process any more requests. So it has implications on my frontier capacity as well. So that's why I use optimize for speed for synchronous requests and optimize for throughput for asynchronous requests. And I see there's large list of questions, and unfortunately we ran out of time. I have my email address on this last slide. Feel free to send me questions. I'll try my best to answer them, as many I can. and hopefully you guys learned something out of this session, and I really appreciate you guys taking your time out and listening to this session. Thank you, everybody.
Well, thank you so much for the insightful presentation, Mr. Gurinder. It was a great session. I would also like to thank all our participants for the support in making this webinar a success. The recording of this session would be available on techgig.com by Monday. Thank you all. Have a great day.